Today's lesson is on the counting principles, and these are also, we're going to have some principles like combination and permutations in here. So fundamental counting principle is, let's say we have two events, E1, E sub 2. The first event can occur in M ways, and after E1 occurs, E2 can occur in M2 different ways. The number of ways that they can occur together is M1 times M2. So pretty basic. Examples of these would be, how many different ways can we draw a card from a deck and flip a coin? Well, 52 card deck. Flipping a coin, there's two options there, and you just multiply. 52 times 2 is 104, and 104 different outcomes or possibilities. Next, rolling a 6-sided die, flipping a coin, and picking a letter from the English alphabet. Again, we've got two options for a coin, heads and tails. There's 26 letters in our alphabet, so doing 6 times 2 times 26, we get 312. Next, how many different 7-digit phone numbers can be created where the number does not start with 0 or 1? So we've got 7 positions. Digits generally mean there's 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10, right? 0 counts as well. But for the first digit, we can't start with 0 or 1. So we have 10 digits, subtract 2 for 0 and 1 to get 8. Doing that multiplication, we're going to have 6 zeros with the 8 in front, so 8 million is our answer. Then one last one, how many different outfits could you make if you had 8 different pants, 10 different shirts, and 5 different shoes? Right, so that will have completely different outfits. So 8 times 10 times 5 is going to give us 400 outfits. So permutation, right? A permutation of n elements is, different elements, is an ordering of the elements such that one is first, one is second, one is third, and so on. Basically, we're getting to factorials in a second here, but what we're talking about here is order matters when we're doing permutations. If you remember, combinations are probably something you've also learned. That one, order doesn't matter. So we'll talk about permutations first, and then combinations kind of come in next. So number of permutation of n elements, right? It's basically how many different ways can we rearrange n elements. And the general answer is n factorial. Well, what does that mean? That means that number times the number below it times the number below it until you get all the way to 1. I mean, 2 factorial is 2 times 1. But if you have like 100 times 99 times 98, and so on, until you get all the way to times 2 times 1. Okay. I'll show you where this is on your calculator in a little bit here. So for example, 10 horses are in a race. How many different ways can the horses finish? Now, typically in a race, order matters. Finishing last doesn't get the same benefit as finishing first, right? So we've got 10 factorial, which is 3,628,800, which again is 10 times 9 times 8 times 7 times 6 times 5, so on. Okay, now in your calculator, we'll try to get it centered here. Okay, and clear it out. We've got the factorial button. So I do 10, and then we're going to hit the math button. And then we're actually in the probability section. So we move over to the right 3, or I guess we can go to the left 2. And option number 4 is that. So we could either click down or you could click 4 as your shortcut. And that will give us the 3,628,800. Next, 6 people stand in a straight line. How many different ways can they stand in a line? If you've got your calculator handy, go ahead and try this. The answer is 720. Next, we've got permutation of n elements taken r at a time. And this is where NPR comes from, right? This is most common use of permutation, I would say. So, like say we have 20 elements, pick 4. That was the same mathematically as 20 factorial over 20 minus 4 factorial. Now, how would that work out, right? And you're seeing this is, well, n times n minus 1 times n minus 2 till we get n minus r plus 1, right? And here's a better way to think about it, right? Again, this is a button in your calculator we'll also see and use. But let's say we have 5 permutation 3. Okay, so 5 pick 3. We're picking 3 of the 5 elements. We're picking 3 at a time. How many ways can we do it? So there's 3 blanks, right? So in this case, if whatever r is, that's how many blanks there are. And then we start at 5 and count down. So 5 options for the first, 4 options for the second, 3 for the third, right? This would, an example of this question, like why would you use 5P3, would be, say we had a race with 5 kids, and the first 3 kids, how many different ways can we have the first 3 finishers, right? And it would be 60 different options of the first 3 finishers. Couple more questions. 10 horses are in a race, similar to before. How many different ways can they finish first, second, and third? Right, so 10 horses, and again, race, order matters, permutation, 3. Okay, and now mathematically, this is how I learned and taught students it in 7th grade. That, again, there's 3 blanks, 10 times 9 times 8. As we get to larger numbers, it probably makes more sense just to use your calculator. If you don't have the permutation button on your calculator, you'll want to use it this way, but most calculators do. So for example, on TIs, generally you're going to hit that math button again, but first there's 10 positions. So 10, hit the math button again, go right back to the PROB section, and PR right here. So 2, and then we wanted to pick 3, enter, 720. So it does that math for us, nice and neat. 720 is our answer, check, match. Next, 30 people are applying for a manager position at a local Walmart. Once the manager is chosen from the remaining candidates, an assistant manager will be chosen. How many different ways can this be chosen, right? So we've got 30 people, and we're picking 2 positions, right? They're going to pick the first position first, so you have 30 options first, 29 left for the second, so that's a simple math there, and our answer is 870. Okay. Distinguishable permutations. Now this comes into effect when you have characters that are not unique, right? So we'll do a couple examples of these, but if we had 4 identical red balls and 6 identical blue balls, and what would be the different options for picking 3? Well, you know, or for, you know, picking a unique set, yeah, of like 2 or 3 or whatever. And then we'd have to factor in that, well, a lot of those the red balls are going to look the same. The blue, whatever, are also going to look the same. Okay, so how we deal with it in these is basically how many ways can the letters in that be written? AACH, AAHH, ACY, right? So what we do is count in the letters. So usually I get my pen out here, 1, 2, 3, 4, 5, 6, yep, counting in Precalculus, 7, 8, 9, 10, 11 letters. So we've got 11 factorial on top. Now we need to divide by how many times does A repeat? Because when I could intermingle this so many times already and it would still look the same. So we've got 1, 2, 3, 4, 5 A's. So I need to divide by 5 factorial because of the A's repeating. And now C's, we got 1, 2 C's. So I need to divide by 2 factorial for my C's that repeat. Then we got 1, 2, 3 H's and H's. Now, what about the Y's? 1 factorial is 1. So I'm not going to do it unless they have a repetition of more than 1. Putting this into the calculator, we get 27,720 ways we can rearrange those letters distinguishably. Next, how about precalculus? So go ahead and try this out if you feel like you've got it. And the answer is going to be, we've got 11 letters again, 3, 6, 9, 10, 11. We've got only 1 P, we've got only 1 R, only 1 E, 2 C's, 1 A, 2 L's, 2 U's. So I've got 3 things that repeat twice, and we're going to get 4,989,600 ways. Moving on, now combinations. A combination is out of a set of n elements. It is a way to group r elements at a time. And combination is order does not matter. For example, if we had like 7 different, let's say we had 7 different pizza toppings, and you know, a pizza that is pepperoni sausage is the same as sausage pepperoni, right? So because those are the same thing, we're going to have to divide by the number of ways those could happen. And so how combinations work is basically you're doing the permutation in the numerator, and in the denominator you're dividing by the number of ways those those elements could be rearranged. So 7 combination 3, right? 7, we're choosing out of 7, choosing 3 In a combination method where order doesn't matter, we'd have 3 blanks on the top, 7 times 6 times 5. Now, these could be the same, right? Again, if we're making like a group of 3 people and we had 7 people in class, you know, let's say Joe, Bob, and Phil could be picked multiple different ways, right? They could be, and since order doesn't matter, it could be Joe, Bob, Phil, could be Joe, Phil, Bob. That would be the same group, right? Just because I switched the names around doesn't matter. So we do this calculation up top, which is basically the permutation right here. And then we have to divide by how many different ways can we rearrange and get this exact same group. So I've got 3 blanks up top, 3 on the bottom, and we're just counting 3 and down, right? We had 3 blanks, so 3 times 2 times 1, and then this will give us 35, right? 35 different unique groups we could have. How many different ways could 3 letters be chosen from A, B, C, D, E, F, G? And the order of the letters is not important. So counting 3, 6, 7, this is 7, choose 3. In your calculator, this is the same section, 7, math button. We'll switch it up, we'll go to the left this time. And then this is the C, NCR. So I can hit 3, and choosing 3, we get 35. And that was a mistake. 35. I must have hit the permutation button. Because order is not important. If I was a permutation, then that could have been possibly 7 times 6 times 5. Could have given us that 840. So 35. Order doesn't matter. How about here? A standard poker hand consists of 5 cards dealt from a deck of 52 cards. How many different poker hands are possible? Okay, so you've got 52, choose 5. Calculator gives me almost 2.6 million. 2,598,960. And lastly, how many ways can you get at least 3 of a kind in a standard 5-card hand with 52 cards? The hand can be better than 3 of a kind. So we're going to solve for if we get 3 of a kind and if we get better than 3 of a kind, which would be 4 of a kind. So how does that look? Right? We're going to have 13 different cards. So again, just a note, in a 52 card deck, right, just a little note in case somebody hasn't played card before. There's 4 different suits, is what they like to call them. So we can have diamonds, which are typically red. We could have hearts. Sorry for my sketching by mouse. So both of these are the red options. And then we could have, oh goodness, this is going to be hard. We can have spades and clovers. There's a really rough version of spade, and you've probably seen a 3-leaf clover, and it looks a lot better than that. But there would be we'll come with more like broccoli. A clover, and each one of these have cards 1 through 13, right? Basically, if we count ace as 1, and then they've got numbers 2 through 10, and then jack, queen, king. Because these will be brought in another lesson as well when we get into 8-6. Right, so ace, 2 through 10, jack, queen, king. Generally aces are high, but it doesn't matter just for this hand. So we've got 13 different cards that we could have 3 of, right? There are 4 of each card because there's 1 diamond, 1 heart, 1 spade, 1 club of each of these cards. So out of the 4 options, out of the 4 cards, we're going to pick 3 of them. So there's a couple different ways that can happen. So 4 choose 3, or 4 combination 3 is going to be that way. And then we have to pick leftover cards. So this gives us 3 cards. What about the other 2 cards? So we're going to take out these of these options. We're going to take all 4 out because even though we only picked 3 of them, we're only doing 3 of a kind. And so now we have 48 cards left that are not, maybe it was an ace, maybe it was a 2, whatever it was, they got 48 other cards that are not that type. We're just picking any 2 of those. And that would give us all the ways for 3 of a kind. For 4 of a kind, we're going to have 4 choose 4. So we're picking one of these, ace, 2, 3, 4, 5, 6, 7, whatever, queen, king, right? There's 13 options. We're just picking all 4. So 4, choose 4 of them. And then we have 48 cards left, choose 1 for 4 of a kind. Doing this math, we get 13 times 4 times 11, 28, plus 13 times 1 times 48, for a total number of 59,280 ways of getting 3 of a kind or better. That wraps up today's lesson. If you have questions, please shoot me an email.